Okay, welcome to the second day of data mining at Google. Today I'm going to get through so the first part of Chapter 2 in the textbook. The first thing I'll mention to you is that there is a homework that I gave the students that are taking it for credit. And if some of you are interested in doing that homework, what I can do is I can email the solutions to you. I actually have the solutions ready. It's linked from the web page. I'll go online and show you where that link is right now. And like I said, if you want to go through and do some of those exercises, it's meant to cover chapters 1 and 2, so you can go ahead and do those. Let me take a peek at the web page, and I can show you what's up there. It's one problem from the textbook, and then 4 problems that I wrote down. It shouldn't be sort of, pushing the limits of anything too much, but it should give you some review of things that we're covering in the lecture. So let me navigate there right now and just quickly show you that. Okay, so you want me to talk in the mic? Okay. So if you look here on the web page, we have homework right there. Chapters 1 and 2 homework is due Tuesday. That's a week from Tuesday. If you look at the homework assignments, the first thing is just to read chapters 1 and 2. Now, chapter 2, you don't really want to read section 2.4. That's measures of how you measure distances between attributes. There's a lot of material there. We'll get to it when we talk about clustering. So just the first 3 sections of chapter 2 and then all of chapter 1. 1 and 2 that we talked about last time, I just mentioned to think of some different examples. Then textbook problem number 2 from chapter 2 on page 89. Then the last 2 questions, I give you some sort of toy data sets and ask you to do some exercises with those to get you familiar with using Microsoft Excel and R. So you can take a look at those, and if I forget to, remind me to send around the solutions for those, so if you want to practice doing some problems. Okay, so that's the homework assignment. We're going to get into chapter 2 today. The title of chapter 2 is generically called Data. So the first question is, what is data? Well, we're usually going to try and force data into looking something like this matrix that you see up here. And we give different names to the rows and columns, and we associate different things. So generally, so if you can't hear me, let me know. I'm going to talk as loud as I can while still writing on the whiteboard, and hopefully you can hear me. Okay, so think of the data as being a matrix like this. So the rows, okay, we call the rows, some people call them objects, okay? Some people call them...
Sorry, we can't hear you remotely at all when you step away.
That might be because this mic isn't on.
That's just for recording. This room is terribly set up.
So, okay. So the rows are going to be called objects. What else do we call the rows? So they call them objects up here. That's what your textbooks like to use. I like to call them observations. Okay, and that's probably more common in stats, observations. Other names that are given to them: record, point, case, sample, entity, instance, and then observation. So in this toy data set they have up here, the rows are probably people, right? And you see then the person either got a refund on their taxes or they didn't. They're either single, married, divorced. They have their taxable income listed there, and then whether or not they cheated. Now each one of the columns, okay, so the columns, your book tends to call those the attributes. I tend to call them variables. Other people will call them fields, characteristics, features. Sometimes people will call them predictors, but generally designate one of them as being the response. In general, those are the columns. And then a collection of attributes describes an object. So I think I've covered everything on this slide. Now this is just a toy data set, and you can think about how might you use such a data set. Again, you might use this to sort of use these as example data and then try and generalize a rule to predict how likely someone is to cheat on their taxes. So when they say, these are the things that raise a red flag for the IRS, that means that they have some sort of a predictive model so that they think based on your attributes, you're likely to cheat on your taxes, and so they're going to try and audit you. So this is sort of a toy example, but you can think about what the real data would look like. I want to sort of move away from the toy example and show you a real data set. So the first real data set we're going to look at is right here on the web, stats202.com/stats202log.txt. And this data set is basically the web logs from the stats202.com domain and a couple other domains that I have registered. And it's from one day in particular. And I think it happens to be the day where I made some announcement about the class, so there's a lot of data there. So it's from actually June 19th, and you see the earliest date here is like 31 minutes after midnight, and then it goes all the way to the end of the day, 3 minutes before midnight. Okay, so a full day's worth of web logs, and I'm just simply going to save this somewhere on my machine, and I'll talk about how we can open it using R and using Excel, assuming you're using a Windows environment. I think someone sent around an email the other day about how to do this on the Linux environment. So there I have the file sitting there on my desktop. What do I say to do now? So I say right-click on it and say Open With, and then say Microsoft Excel. So I'm going to go ahead and do that. Of course, you could open the Excel application first and then try and open it from there, but let me just right-click and say Open with Microsoft Excel. Now, when you do that, those of you who are familiar with Excel will realize something has gone terribly wrong. What happened here is all the data is in the first column, right? So the first column has all this data. The second column has no data. Even though it looks like the data is going all the way across, that little FX you see up there at the top of the screen, that is actually what's showing you what's in the first column, first row. So the first column, first row has all this. If I mouse over to the second column, first row, you see that there's nothing, right? This is just all carryover from the first column. So what I really want to do is make sure I get these things in the right columns, right? I want to have each attribute be in its own column. So just to sort of get caught up with the slides here, I said right-click, open with, choose Program, then choose Excel, and I said, oops, everything is in the first column. So what is the solution here? Well, the solution is, we need to get the columns separated in the right way. So the solution is click on the first column, and then there's this thing called Data and Text to Columns that's going to do the trick for us. So how do I do that? I go here, click on the first column, which is where everything is. I go to Data, and I say Text to Columns. OK. First thing it's going to ask me, is it delimited or is it fixed width? Now, I think those are self-explanatory, and it sort of tells you what they are right here. This turns out I can treat it as delimited, and then I'm going to click Next. And it's not tab delimited. It's actually, I can use this one as space delimited. Okay? And then this text qualifier, we'll talk about in a little bit. But you see, once I do space delimited, it sort of draws these previews, and at least the first few rows look like it separated them correctly into columns. And you can scroll down and look at some more examples, but assuming the file is made consistently, it should be OK. So I click Next. Then I get to sort of mess the types of these. They're all defaulting to general, and I'll talk about types of attributes in Excel later. But I'll just leave them all as general, and I'll say Finish. And now you see the data looks nice, right? The first column looks like it's some sort of IP address. These columns seem to be missing most of the time. This is the date. This is a little extension there. And then you have some other information. These two are numeric. This is the URL. So these people are going to my home page. These people are going to stats202.com. Then it looks like this might be, I think, the refer, and then this, probably a lot of you know more about this, and this is sort of what type of browser they're using. OK, so I have data from the weblog, and I've read it into Excel, and I think that catches us up here. Let's see, I said click on the first column, say Data, Text to Columns. I choose Delimited, and I tell it that the space is the thing separating the columns. So this is a space delimited file. Basically, wherever I see a space, I know to split the column on that. Now, one question that comes up when you do this is sort of, why did this work, right? Because what's curious is that some of the columns that I've created themselves have spaces in them, right? Like if I mouse over to right here, the browser type, clearly there's a space between, between Windows and NT, right? There's a space there between Windows and NT. So why did it not split that one as a column? Now, I think many of you know the answer to it. The answer is that it is quoted? Right. There are quotes around this. So you don't see, right? You don't see any quotes here in the file, right? There's no quotes there. However, if you actually go back and you look at the actual file itself, you can see, of course, that whoever makes these weblogs is smart enough. Whoops. Oh, I have it open already, right? That's what it's complaining about. OK, let's look at it here. You look in the file itself, and you see, right, these quotes around a lot of these attributes. So in particular, this one I'm talking about, the browser, Mozilla 4.0 space, right? There's quotes around that. So it knows that whenever you see a space, if it's within quotes, not to break the column there, okay? And so that's the answer to my question, why this work. It's escaped using quotes, right? So wherever you see quotes, if there's a space in between the quotes, you don't break the column there. Now, of course, that raises the question, what if you want to have quotes in one of your columns? So then what do? You escape the escape character, right? So this sort of, can get a little bit tricky, and sometimes you wind up having 4 or 5 quotes just to do certain things. But many of you are familiar with this if you worked with data, especially here where we work with a lot of, types of URLs and things, or not URLs, but other things that can have spaces in them. If you read the wiki article on delimiters, you can learn a little bit more about this. But I'm embarrassed to admit how late in life I learned this, but a lot of you have already worked with real data, so you're probably used to doing that. And as we opened it with Excel, you saw that it did say that the quotes had a special function, and that's exactly what. And that's a very common convention, to have some sort of character like a space or a comma or a tab that separates the columns, but to escape it using quotes. That's a very common behavior. So that's sort of how we read data into Excel. Any questions about anything I went over with that? Okay, so that may be familiar to many of you. So we have our data set in Excel. Next thing, how do we read the same data into R? Excuse me. Well, we've already downloaded it, so I don't need to do that. The first thing I usually like to do is do this setwd command. That saves me from having to specify the full path every time. And literally what that means is I'm setting my working directory. So let me first open R. Excuse me. Hopefully many of you saw the thread that went around about the R installation on your machines. So I've opened R here on my Windows machine, and I'm simply going to set my working directory to be my desktop, which is where I save that file. And so I do that. Now anything that I save, anything that I load, I don't need to specify the full path. It's just going to assume that it's here in this directory. And you can specify any directory you want there. The only thing that makes it tricky is if you move things around later, you might have to change that command if you have it hard-coded into your script. Okay, so that sets it there. Then let me close this version of it so it doesn't complain to me again. Okay, so now I'm going to read it in. Now the command I'm going to use to read it in is the read.csv command, and I'll say a little bit about this syntax. Maybe I'll just say this. Okay, so what did I do? I said read.csv, that's the command to read it in, CSV file. Then I quoted the name of the file, which was stats202log.txt. The next argument was the separator. By default, CSV defaults to comma separators, so I told it that the separator should be a space. Header equals false, meaning that the first row of the data set does not give me column names, right? Sometimes the first row of your data set just gives you names of the columns. This time it doesn't. I say header equal false because I think the default is true. If you want to know more about any one of these commands, like setwd or read.csv in R, it has very good help. The Windows version, if you type $, and something like read.csv, which is the command you just used, it'll give you sort of, well, read.table, read.csv, these are all similar things. And it tells you about the different arguments. And you can see here that, in fact, read.csv does default header to true. And so if I hadn't changed that to false, as I did, what would have happened, it would have basically not given me the first row. It would have used the first row as the header columns, which wouldn't make much sense. And you see, of course, the separator defaults to comma, so it's a good thing I changed that to quotes. So the help is very useful for these commands, but you sort of have to know what the command you want is first, because sometimes it's hard to know. So read.csv reads the data in for me. Now let me tell you one other thing I did here, right?
Can you just clarify that
yeah.
minus sign is a prompt continuation and not what we're supposed to type?
Let's see, yeah. So what you would type would be, yeah, sorry. What you would type would be exactly what I have on the slide. And so between the comma and the separator, you're right, that plus is just a continuation that it was pulled onto the next line. Okay, that's what you're asking about? Okay. Okay, yeah, so this is literally what I type. Now, the other thing I wanted to say about what I typed here, and sorry, this is the prompt sign, so I'm not typing that. I do type, though, the data with the less than and the minus. And what does that mean? That's an assignment in R, right? So had I just typed read.csv, it would have just output to the screen, right? It would have just showed me everything in the file all at once. If I just type read.csv without that assignment, it just spits it all out at me. So when I do that, it's basically assigning the object called data, and I didn't have to initialize it or anything. I just call it data. You can call this whatever you want, and I assign this data set to the object called data. Okay, so now R has in its memory an object called data that is assigned this data set. Okay, so that's generally how we read the data into R. I mean, there's other variations of this, if you don't want to use up the memory or if you want to specify the path directly and not have to have 2 copies of it floating around, you can do that, but that's generally what we'll do to read the data in. Any other questions on that? Okay, so now let me go to the next slide. I say, let's look at the first 5 rows of this data. Okay, so R is not a spreadsheet application like Excel, but we can view the data. And here I typed, notice I typed data 1:5, comma. Okay, let me explain what that means and what it does. So basically, if I want to see the first 5 rows, I would say something like data 1:5, comma, with this argument blank, okay? Basically, it thinks of the data as like a matrix, right? So you're telling it which rows you want and which columns you want. So if I want the first 5 rows, I say the rows are 1 through 5. If I want all the columns, I just leave that argument blank, right? Okay, so those are the rows and those are the columns. And in R, something like 1:5 is just means literally 1 through 5, right? So I'm telling it rows 1 through 5, columns, everything, okay? So if I do that, I want to see data 1:5, the first 5 rows, and all the columns. That's exactly what I get, okay? And you have to scroll here a little bit to see that, now notice it's given the column names, it's given these, it's made up these attribute names, right? The first attribute is V1, V2, V3, then V4, and then I see the row numbers 1 through 5 right there. And so it looks like it's done a good job of reading it in, and I can look at the first 5 columns and make sure that the first 5 rows and make sure all the columns look like they're reading in the right thing, okay? So that takes care of what I have on this slide. Then the next slide I say, suppose I want to look at the first column. Well, for that one, you can imagine you would just type data and give me all the rows, so I leave that blank, but give me just the first column, right? So that's going to give me the first column. Okay, now the first column looks like some sort of an IP address, right? So we can confirm that if I say data, comma 1, just the first column. It spits out all these IP addresses at me. And notice it's giving me still the row numbers. So 1921, so then the last one must be 1922, which confirms that there's 1922 rows in the data set. Now it also says something different, which is going to come up a little bit later. It says 73 levels. And it kind of lists them. It lists this one, this one, this one, dot, 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 and then the last one, okay? Well, I say the last one, and okay. So these are 73 unique values of the IP address in the first column. Now, it's sort of interesting that it's doing that because it knows that this variable is not something that's numeric, that it has distinct categories, and we'll talk about that in a second. Question? Everything is 1 indexed in R, okay? The only thing, though, you can still get yourself a little bit confused in both R and Excel because if you, especially in Excel, if you have a header row, then everything kind of becomes 2 indexed, right? Because your first row is always your header sometimes. So you have to be a little bit careful with that. But in general, R is always 1 indexed, and so is Excel, but be careful with the header row. Okay, so we have the first column there in R. And I think, yeah, that's all I wanted to say about reading the data in. We'll play more with this data set a little bit later on, and we can see what's going on in the stats202.com web logs. But that should give you sort of pretty much the information you need to sort of read a data set into Excel or read a data set into R. Now, of course, there's data sets of more complicated structure that we're not talking about, but assuming you can sort of force the data into looking like this matrix with the different rows and the different columns, then this will do the trick for you. And obviously, that's kind of what R and Excel are hoping for, especially Excel being a spreadsheet application is sort of hoping that it can look like a nice matrix. Okay, any questions about reading data into R or Excel? Yeah.
In the API, you specify header equal no, and
Yeah.
you specify header equal to yes, and is that for reading the data with the named column?
Exactly. So the header equal false versus the header equal true. Suppose your data set, the first row had column names. Then you would say header equal true or use the default. And whatever it sees in the first row, it's going to use for the column names. Now, of course, there has to be as many entries there as there has to be in the other rows, but it will use that as the column names. And by default, you would get a bad behavior. If you let header be true and the first row is really an object, then that object becomes the column names, which is not what you want. Okay. Other question?
If you wanted to say columns 1 and 3, is there a syntax for specifying that?
Right, so he wants to see just columns 1 and 3. So in R, there's this, and I'll talk about this later, there's sort of this C thing, which sort of creates a vector, right? So C 1, 3 is the vector 1, 3. So if I said data and I wanted all the rows, but I wanted columns 1 and 3, that would be the syntax that would give it to me. Okay, so here, let me just do the first 5 rows, but columns 1 and 3. There you go. You get V1 and V3 out. Okay, so again, you just index into it like that, but yeah, you have to combine the 1 and 3 with this little C operator, and I'll talk more about that C operator next time. Any other questions about reading data into R in Excel? Okay, so the next thing I want to talk about, if we're going to be working with this real data, we have to know what kind of data we're getting. And it's very interesting that the textbook doesn't talk about this, right? And I think this is sort of, one of the criticisms about data mining is that they, I don't want to say ignore this issue, but it sort of becomes a non-issue. So what am I talking about? There's this big distinction between experimental data and observational data. And you notice that I say up here, I say, most all data used in data mining is observational data, so be careful, right? So observational data is data that can often get you in trouble, okay? And so what's the difference between these? Well, I put sort of some definitions up here, but I think most of you should sort of get this just from thinking about, the difference between collecting data in an experiment versus the difference between collecting data observationally, right? So experimental data, basically you exercise careful control, right? So think about experiments that you do here. You say, well, I'm going to randomize whether or not this person is in the control or the treatment. I'm going to be very careful about anything, and just be very careful, right? You have very careful control over the data. Whereas observational data, you really don't know too much about the data. Observational data. You really don't know too much about the data, and you really don't know what's causing someone to be in one group or the other. So there's basically no, or we could say little control over the attributes. Okay, now why is this important? Well, I'll make it obvious through some examples, but the whole point is that the data is going to look the same either way, right? Regardless of how the data is collected, it could look the same to you, but whether or not it came from an experimental setting or an observational setting will influence sort of what conclusions you can draw from it. In particular, you have to be very careful what conclusions you draw from observational data. However, in data mining, it just has this observational feel to it. If you think about the types of data we were talking about last time, it was just sort of data that happened to be sitting around anyway, and so we were going to look at it and see what kind of information we got from it. It wasn't data that we said, I'm going to do an experiment to collect this data. It was data that happened to be sitting in a database, and I was going to see if I can find any information in it. So how can this get you in trouble? Well, I have a couple examples up here just to mention how it can get you in trouble, and then I think it would be pretty clear, right? So the first one is the Diet Coke versus the weight, right? So what's going on in this data? Well, in this data, my observations, okay, are people, right? So I have people, person 1, person 2, person 3, person 4, right? These are my objects, these are my observations, these are people, right? And then I'm going to have 2 attributes, or 2 columns, or 2 variables, right? The first one might be like how much Diet Coke they drink. Let's express it as like a ratio or a fraction of all Coke consumption, right? So this person, when he drinks Coke, 90% of the time it's diet, right? And this person, when he drinks Coke, only 5% of the time it's diet, okay? So let's do it like that. And so let's assume all these people are people that at least drink some Coke, right? And so, this guy is the guy who seeks it out, and this guy, he only drinks it, when they're out of the regular Coke. He hates the taste, but if he's thirsty, he'll drink it. Okay, and then we record their weight, right? Okay, so this person, he's kind of a big guy. He weighs 200 pounds, and this guy, he's pretty skinny. He only weighs like 145, right? And so on, and you get lots of observations like this. Okay, so now my point is that you can collect this data in a lot of different ways, but it will still look like this, okay? So what are the 2 different ways you could collect it? Well, one is observationally, right? You just go out and you get people and you say, hey, how much of the time do you drink Diet Coke versus regular Coke? Hey, how much do you weigh? You just collect the data, okay? That's observational data. Another way you could collect it would be the following, okay? You get a whole bunch of people and then you randomly tell them, look, you're going to drink 90% Diet Coke. You're going to drink 5%. You assign them, right? In fact, you could just split it up and say, 10% of the people are going to drink 10% Diet Coke, 10% of the people are going to drink 20% Diet Coke, 10% are going to drink 30% Diet Coke, et cetera. You control it, right? That would be the experimental setting. Okay. So the same type of data can be collected in 2 different ways. Now, why does this matter? Well, let's think about what you might look at with this data, right? You have 2 variables, so we might plot them against each other, right? So on the bottom, we put here Diet Coke consumption. And on the top or on the y-axis here, we put their weight, okay? Now, let me ask you the following question. Okay, so if I were to collect the data observationally, right, simply asking people, how much Diet Coke do you normally drink, and how much do you weigh? Do you expect 1 or 2? 2. You expect the more Diet Coke they drink, the less they weigh. Okay.
Or the reverse.
Or the reverse. Or the reverse. So
People bother drinking Diet Coke.
right. So it could go either way, right? And so you expect maybe you would see this. Someone said maybe you can see this. But there's also an argument for the other way. Let's talk about the argument for the other way, right? I see this one, okay? Now, suppose I see this one. First of all, let's talk about what would be the wrong conclusion from this data. The wrong conclusion, right, is to say that like Diet Coke is making you fat, right? They're putting some ingredient in there that just makes you fat and just makes you, have to buy more Diet Coke, right? Okay, somehow this is a bad thing to drink. You should lose weight by drinking regular Coke, right? Because as you drink more regular Coke, okay. So that's, of course, the wrong conclusion. But how can this happen? Well, look, if I'm a skinny guy, why am I wasting my time drinking Diet Coke, right? I'll just drink regular Coke. I don't care if I gain weight. That might actually look, better if I gain weight. But if I'm trying to lose weight, so you get the point, right? So the point is, if this is observational data, this is quite possible. But the problem is then you can't infer any causation, right, from the observational data. You cannot infer the causation. You don't know that drinking more Diet Coke causes people to weigh more. And in fact, in this example, it doesn't. So the observational data would look just like the experimental data, except I can't infer any causation from it because I didn't really do the experiment. Okay? So you have to be very careful. The data is going to look the same, but how is it collected is important. The data doesn't tell you how it's collected. The data is just sitting there in a database. You have to know how it's collected, and you have to be very careful with this distinction, and they don't really address it all in the book. Let me give you the one other example, which is sort of timely, and I think it's sort of cute. So this is, quick comment.
So you said from observation data you cannot conclude anything. Maybe just attribute that it's not right. For example, it's a weight increase or weight loss. Not it's a weight data, not like an absolute weight. You might.
Right. So the thing is, you might be able to measure other things that will be more insightful. So I'm not saying you can't conclude anything. I mean, you would wind up with a statement where you would say, increased Coke consumption is associated with higher weight, right? Associated with, as opposed to causation. And that could be quite useful to you, right? If you have a game where you're trying to predict how much someone weighs, and all you get to know is how much Coke they drink, it could be quite useful to you, right? If it's really a prediction problem where you're just trying to predict their weight, and you just get to find out, how much Coke they drink, right? It could be quite useful, but you just have to be very careful about the causation. So, okay, and then like you say, you could measure other things which might clue you into the causation. But with just the two attributes, it's a very murky picture. Okay, so this one, the carbon dioxide and the Earth's atmosphere, carbon dioxide in the Earth's atmosphere versus Earth's temperature. So this is the picture, right? You say like, look, every year I'm going to plot, how do I do this one? I'm going to plot how much CO2 is in the atmosphere, and I'm going to plot the temperature. Okay. And what do I see? Well, in 1920, we had, low CO2 and low temperature. 1940, it was a little bit higher, et cetera. Now we're in the year 2000, and we have a lot of CO2, and the Earth has really started to warm up, right? So you see this picture, right? It's going up. Okay. So, some people will say, this is proof, right? You guys are causing global warming with your cars and your SUVs and your computer usage. You guys are all causing global warming, right? Because don't you see that the higher the CO2 is, the higher you have caused the Earth's temperature to be. Okay. Now, some people will use the exact same data and say the following. What's really going on is the Earth's temperature has been increasing. It increases sometimes, decreases sometimes. We used to have an ice age. Greenland was called Greenland because it used to be green, and then it got cold and froze and all these things. They'll talk about Earth's temperature just changes, and lately it's been going up. And if you know anything about gases, when these gases that make up the Earth's temperature are hotter, they can hold more CO2. So they will make that argument. They will say, of course, these things are associated because increased temperature causes more CO2 to be absorbed in the atmosphere. Now, who's right, who's wrong? The point is the data doesn't tell you that. It's not experimental data, right? You haven't artificially changed the Earth's temperature to see if it would go up. You haven't artificially increased the CO2 to see if it would go up. Now, there's other data that could answer that, right? If you see one lagging the other, there's other data. But the point is, just looking at the two attributes observationally is not proof enough. You haven't replaced the scientist with your data, right? You still either need to do the experiment or you need to have some understanding of which variables are really causing other variables. The data alone does not tell you the whole story. Okay, so these are my two examples to sort of warn you about the difference between experimental and observational data, and to just know that when you get data in data mining, it's most often observational, so you have to be very careful about the conclusions you draw, especially with regard to causation. Okay, any questions on that? Question?
So correlation is not causation.
Exactly. That's it. That's it. Basic
But
bottom
also,
line.
This seems to be vaguely related to possible sampling biases, not the two examples you gave at the general discussion. Say I stop people and ask questions, and half of them just walk away, saying, don't bother me.
Right.
So I end up sampling those who are interested enough in what I'm asking.
Exactly. Now, so the more carefully you do sampling, the more it can look like an experiment, and the line can be a little bit blurry. So I can get really good observational data that is almost good enough as an experiment. So that's the point, right? And then your first point about correlation is not causation, you're right. That's the Stats 101, and I'm just sort of telling you the story. It's curious, though, that they left it out of the book, because I think a book on data mining, anyone has to say, be careful about that, because if nothing, data mining is looking at observational data. Okay, any other comments, questions on that? Okay, so the next thing to talk about with attributes is whether it's qualitative versus quantitative. This, you've probably heard this before, it's the distinction between categorical and numerical, which other words, I prefer the textbook uses qualitative and quantitative. So this is sort of, not that deep, and you probably understand it just from saying what the words are, right? Categorical, what your book calls qualitative, right? Or categorical. Basically, these are categories, not numbers, okay? Let me just call this categories. So you would not add or subtract these things, right? If I say like, this is my home phone and this is my office phone, okay? They're both numbers. And you say, oh, there's a 50% chance he's at home, there's a 50% chance he's in his office. Let me average the two and call that number, right? There's no point, right? Those numbers have no meaning, right? So an example here would be phone number. Even though it looks like a number, it's not really a number. Right? Something else would be, zip code, right? I don't usually say, oh, the difference between these two zip codes is something, so, what does that mean to me? It means nothing. The numbers are pretty meaningless, right? Eye color, letter grade, those are obvious. They don't even look like numbers. But something like IP address or zip code or phone number, those look sort of like numbers, and you might be tempted. Now you say, well, that sounds really stupid, right? No one's going to average two phone numbers. But you have to be careful, right? The software you're using is going to be a black box algorithm, and it's going to see a number, and it might start treating it as such, right? If you give it a zip code, or you give it a phone number without the dash in it, or you give it an IP address without the little decimals in it, it might treat it as numeric, and that's the wrong thing to do. So as data becomes electronic, even something like eye color, right? You have eye color, and you code it, brown is 1, blue is 2, green is 3. Your software might assume that's actually a number, and it's not. So you have to be careful about that distinction. And then, of course, the other one, which is what your book calls quantitative, that's simply, numeric, right? So these are things that are numbers and can be treated as such. Your weight, failures per hour, number of TVs, the temperature. Okay, these things can be, you can subtract these numbers, you can add these numbers. They're numbers and should be treated as such. But you have to be careful about that distinction, and the textbook talks about it on page 26. Any questions on that distinction? Question?
Using a side note, I once worked at a company where they had to mail like 1 million things, and when they imported the data, the zip code field got treated as a number. So the entire East Coast, whose zip code is prefixed with a 0, the 0 was dropped.
Okay.
So something like 15% of all the mail came back.
Okay, so yeah, if anyone didn't hear that, so his story is someone treated his zip code as a number, and so they dropped the trailing, or the preceding 0, and yeah, it's a problem. And Excel will do that to you. I've had ID numbers in Excel where it wants to chop off the first few zeros, and I have to tell it, look, this isn't a number. Don't treat it as a number. Okay, and you can imagine doing like a regression model, right? The zip code shouldn't be in the regression model as a continuous predictor, right? You're not trying to extrapolate between two zip codes, right? So you have to be careful. Okay, any other comments on qualitative versus quantitative? Okay, again, this is sort of stats 101 stuff, as you say, but as you're using software, you have to be careful about this. Your book also splits up the qualitative or the categorical into nominal versus ordinal, and the quantitative into interval versus ratio. Now this distinction becomes a little murkier, okay? In fact, this is somewhat controversial, but we'll talk about sort of the textbook formulation of it and talk about why the differences are important. So let me just say the qualitative splits into nominal versus ordinal. Ordinal, right? Okay, so what's going on here? So nominal, there's no order, and ordinal, there is order. So let me call it a meaningful order, right? Because you can impose sort of some arbitrary orders. So let's call this a meaningful order. Okay, so the question is like, is there order, is there not? I have examples on the next slide, so let me just mention a couple of them. So nominal, things with no order. ID numbers, right? If there's no information in the order of them, then it's nominal, right? If the fact that someone's ID number is bigger than your ID number means nothing to you, then it becomes nominal, right? Eye color, blue, brown, green. You could order them in the order of the color spectrum, but that probably doesn't mean anything. Zip code, does it mean anything? So you said the lower numbers are on the East Coast. Well, if it means something to you, okay, maybe it's ordinal. But in most cases, something like zip code, the order of the number would have no meaning to you. Basically, you could do sort of a permutation, okay, an isomorphism where you permute all the numbers and you haven't lost any information. If that's true, it's nominal. Okay, things like ordinal would be like, okay, your height, tall, medium, short, right? Medium is closer to short than tall is, okay? Grades, A, B, C, D, F, right? A is closer to B than F is, right? Taste of potato chips on a scale from 1 to 10. If you ask people to rate web pages on some scale, for instance, so that could be ordinal data, right? So basically they're categories, but they have order, okay? So I think that distinction is pretty clear. Now you say there's some things in the middle, right? Maybe I am using the number of the zip code to tell me whether they're East Coast or West Coast. In that case, that one might leak down here. But most of the time you're using zip code, if someone changed all the numbers on you, you really wouldn't care, because all you're really using is them to differentiate distinct areas of the country. Okay, so any question on the distinction between ordinal and nominal? Okay, now most software packages don't really, handling ordinal is a little bit tricky. There's really nothing, well, we'll talk about it later on, but it's not a hard distinction in software packages. The other distinction here for quantitative attributes, we split them into interval and ratio. Now this one is probably even trickier and a little bit more murky, but let me talk about it. So if something is quantitative or numeric, it can be either what we call interval or it can be ratio. Okay, so what's going on? Interval, they say there's no, what they say, true zero, right? There might be a zero, but there's no true zero, versus ratio, there is a true zero. And you can do division. Division makes sense, whereas on the other side, you cannot do division. No division, doesn't make sense. Okay, this is sort of if someone says, there's a 10% increase in temperature. Okay, does that really make sense? Okay, so let me give you some examples here. So things that are interval, right? So most things are ratio. Most of the time, division makes sense, but there's a few sort of special cases that we should consider as interval. One thing would be temperature, okay? Let me give you this argument, right? Suppose that it's 80 degrees this afternoon, and last night it was 40 degrees, okay? And I'm sort of impressed by that, so I call home and I tell my parents, do you know in California it's twice as hot in the afternoon as it is during the night? It doesn't really make sense, right? Because what if my parents live in Canada? Then they'll look up and they'll say, no, it wasn't, right? Because they're measuring in Celsius, I'm measuring in Fahrenheit, and those two scales have different 0 points. So then you say, okay, well, where should the real 0 point be? Well, probably not in either place, right? It probably should be absolute 0, but no one measures, an absolute 0, right? So in those cases, there's no real true 0, so temperatures in Celsius or Fahrenheit are called interval. You can take differences, you can do subtraction, addition, but you can't really do ratios. You can't really divide. Calendar dates, right? Should I start at 1970? Should I start according to, my religion? Something like that. You don't really agree where you start, so differences make sense, but ratios really don't. GRE score, right? If I have a 600 on my GRE and you have a 300, doesn't mean I'm twice as good as you, because where does the GRE start at, like 200 or something? 250, I don't remember what it is, but it doesn't start at 0. So there's no true 0. So the point is, division doesn't make sense, ratios don't make sense. You shouldn't say there was a 10% increase in temperature if you're measuring on Celsius or Fahrenheit, okay? Most things, though, something like the Kelvin scale that starts at absolute 0 is okay. Something is twice as long, that makes sense. Something took twice as long, that makes sense. I have twice as many of something, that makes sense, okay? So most of the time, division is okay, but there's a few cases where you shouldn't divide, and those are called interval. Okay. Any questions about that?
If I'm able to choose a 0, then I can treat anything as a ratio.
Yes, is very tricky, right? I mean, the question about even like calendar dates, right? You could say like, well, it's twice as long after 1970 as, you know. So if the question with that one really is like, how does the 0 really make sense? Is it really important? And if you are referencing with regard to that 0, then it's okay, right? So if you're saying this date is twice as long after 1970 as this date, then the ratio makes sense. But if 1970 has nothing to do with anything, then you have to be careful, because someone else could say, I'm going to fix my 0 at 1950, and your 20% increase is now my 5% increase, right, with the temperature, right? You know, the Canadian is going to argue with the guy from the US and say, no, the temperature swing was only 10%, not 30%. Right? So it has to be like a 0 that everyone can agree on, right? Something like length, right? My foot is twice as long as you. We agree where 0 is. 0 is sort of like where, you know, you have no foot, right? And then it gets longer after that, right? Like I took twice as long as you, right? You can actually see the number 2, right? You would have to do it, you'd have to do it 2 times to equal one of my time, right? We agree on 0, there's no question. Things like this is murkier. We don't agree on 0. And again, the line isn't that hard and fast, but you have to be careful, you know, when someone says, you know, this metric increased 10%. Is the 0 really meaningful? If we can agree that it is, but if not, someone could fudge the data and just move the 0 and say, oh, I made it increase 50% because they redefine their 0. Okay, but it's a sort of a murky distinction. Any questions on this? One more.
Often you'll take a ratio variable and make a difference of it. But it depends on whether you're talking about the ratio value as it or the reciprocal of it. The difference can mean or can grow in different ways. Is there any kind of art to picking the right reciprocal versus not reciprocal?
Yeah, I mean, there's discussion about sort of different transformations of these things and which things are legal and which things aren't legal. And you can lead yourself into some contradictions. So I think I'm just going to leave it at this. Maybe next time I'll point you at sort of the paper, which was from psychology, where they first started talking about these different types of measurements. And I think there are some internal contradictions. It's not without controversy. And so I don't think I want to go down these roads. But it becomes sort of tricky. And how should you transform something, and what is the most meaningful scale on which should I be logging something, and how does that change things, et cetera? Should I take it reciprocal? How does that change things? Is it still meaningful, right? Okay, other questions on this? Okay, so let me go on here to just mention that there are sort of basic arithmetic operations associated with each of these. In particular, something that's nominal, you're only looking at distinctness, right? So it's either equal or not equal. Whereas a categorical variable that's ordinal, you know, we're inferring the order, so less than, greater than, or equal or not equal. Something that's interval, you can do the addition and the subtraction, you just can't do the division. So you have addition, subtraction, you have greater than, less than, you have equality or not equal. And then finally the ratio, you can basically do all 4 things, right? There's nothing stopping you from doing any of these things. The distinction here, I would mention a little bit though. I just wanted to say this. When I was talking about this yesterday, someone mentioned a real, you know, how murky some of this is. Sorry, where's my examples? They said, why is it that the taste of potato chips, which you scaled at 1 to 10, was ordinal, where the GRE score was interval? They said, it seems to me like the differences here mean as much as the differences here. And that's a little bit questionable, but the problem with the potato chip scale, right, is something like if you rate these as bad to good and you just say, you know, like 1 through 2 to 10, the question is the difference between 9 and 10 the same as the difference between 8 and 9? And arguably it's not, right, for the potato chips, because it might depend on how they labeled the scale. Where arguably with the GRE, a 10-point increase on the GRE is supposed to mean the same thing, whether you went from 300 to 310 or 600 to 610. But you can debate that, and that determines whether or not it's in one of these, whether or not the subtraction is meaningful. If the subtraction is not meaningful, then it has to become ordinal. But if you believe the subtraction is meaningful, then you can call it interval. And again, it's quite a murky distinction. Okay. All right. Okay. Any questions on that? All right. Then the next thing to talk about, which should be pretty clear to you, is the difference between discrete and continuous. And you've heard this before, right? So discrete, I like to say that there's some sort of gaps between the numbers. There's like either finite or countably infinite number of possible values, whereas continuous are things like real numbers, right? They're uncountable, okay? And so data can either be discrete or continuous. Okay, continuous. Okay, so discrete, again, there's some sort of like gaps, naturally occurring gaps between the numbers, whereas continuous, there's no gaps. Okay, so that's sort of my short two-word informal definition. What does it say up here? Okay, so again, discrete, finite or countably infinite set of values, so zip codes, right? There's just separate categories, right? You can have a 94550, 94551, but you can't have 94550.2, right? There's nothing in between those two, right? You can't measure zip code more accurately, right? It's just some level of granularity. Things that you count, right? How many siblings do you have? 2. No, exactly how many siblings do you have? No, that's it, right? You can't have like 3/4 of a sister or something, right? Set of words documents. So you have like, you can have a half a sister, right? But you cannot, so same, you can have half a sister, but you cannot, at some point you lose the granularity, right? I cannot have 5/6 of a sister, right? Okay. And it's countable, right? You can give me fractions, but you can't give me floating points, right? Okay. Often represented as integer variables, right? Especially if it, you can usually map these things into integers. Binary attributes are a special case of discrete, right? Binary is a special case with just 2 values. Okay. Binary, is just 2 values. That's a special case of discrete. And one of the homework problems asks you, is it discrete, continuous, or binary, right? Okay, then continuous, these are things that are real numbers. You can compute as accurately as the instruments allow. So you can compute as accurately, I'll probably spell that wrong, accurately as your instrument allows, right? So you have some sort of measurement instrument, and you're just limited by that, as accurately as instrument allows. So, for example, right, temperature, 76 degrees today. Well, it's really 76.4. Well, it's really 76.42. Height, I'm 5'11". No, I'm really 5'11.3", something like that. Now, it's interesting, right? You can say no 2 people are the same height. Because if you really believe it's continuous, there's always some minuscule difference, okay? So if you're sort of do probability, right? What's the probability, if I draw 2 numbers uniformly between 0 and 1, what's the probability they're equal? 0, right? It's continuous, okay? Weight, no 2 people are the same weight. Now, practically, you can, represent these as floating point, and you can practically use a finite number of digits. But again, you really want to have as many decimals as you can if it's really continuous, where if it's discrete, at some point, there's no more information, right? There's just gaps between it. Okay, so I think that's what I wanted to say about the difference between discrete and continuous. And of course, that's going to depend how you treat things in the software a little bit, but for the most part, it doesn't make too big of a difference. Okay, I think that's all I wanted to say there. The one interesting example is money, I think, right? Is money discrete or continuous? So I claim if it's money out of my wallet, it's discrete, right? But in general, if it's money, you could argue it's continuous, right? So how is money out of my wallet discrete? Well, I can have, the textbook cost $80.55 or $80.56, but I can't pay half a penny, right? You can break the penny in half, but it's not worth half a cent, right? There's nothing in between. Whereas continuous, if you compute interest rate, you can compute it as accurately as you want, right? If you say the interest rate is going to be 5 1/3, you can carry as many decimals as you want. But money in your wallet would be discrete. So that would be a good example that's sort of right on the boundary, depending on if you say money in your wallet can only be computed to the nearest cents, whereas discrete can be computed, or whether money in the bank can be computed as to many decimals as you want. Okay, then I will mention here that qualitative categorical attributes are always discrete, right? That should be obvious, right? If something is in distinct categories, it's discrete. The thing that gets tricky is that things that are quantitative can go either way. And the example I gave you the examples I gave you so far are things that were quantitative. They can go either way. So I think you remember that distinction and say that if something is qualitative, that immediately implies that it's going to be discrete, or binary, which is a special case. Whereas if it's quantitative, that will imply that it's continuous. Sorry. That will imply that it's either or. So it could be discrete or continuous. Or continuous. Okay. The next thing I have up here is to go through some of these examples. Actually, this is one of the instructions on here are the same as one of the homework problems, but this is exactly where I stopped on Thursday when I did this. So I'm going to stop here. A couple announcements. Oh, let's see. Let me know if I forget anything. So the videos are up online. They're also, so they're on the Tech Talks, but if you're trying to watch them at home or something, they're also up on Google Video, right? So let's see, Google Video, see if this works. They showed it to me last time. I think it was up there. Why are we so slow? Maybe my connection. Okay, whoa, look at that. Let's see. So, see that. Let's see. There he is. Okay, so that's Tuesday, right? So you can watch that. So those are up online there. And they're also on the Tech Talk. What is funny, right? So, right? Yeah, rate it. What I'm mad about is that, I don't get that recognition, right? You get like this one or something, right? I don't know why that's not any better than this class, right? It's just some guy singing. So anyway, I'll just tell you that the videos are up there. The other thing I was going to say is that the books, they ordered some books. I promised we'd give those away today, but they're not in yet. So, next time if they're in, we'll do a sort of draw randomly. I don't know how many. They have like 40 or 50. I told you about the homework. I don't know. Am I forgetting to say anything? Nothing? Okay. So I'll see you guys on Tuesday. Thanks for coming.